So usually when you think about a threat, right, like a threat to your health or your home, you expect to be able to see it.
Oh, absolutely. Yeah.
I mean, if you've got a crack in your foundation, you can point right at it. You just say, "Ah, there's the problem." Or like if you break your arm, you get an x-ray and there's this bright white jagged line and the doctor says, "Yep, it's broken."
Right. It's super binary. It's safe or it's dangerous. We really, we rely on that visual confirmation. It just gives you the sense of control.
Exactly. But the second you step into the world of atmospheric chemistry, which is what we're looking at today, that x-ray machine is completely
Oh,
useless
totally useless. Yeah,
because we are essentially navigating this landscape of invisible hazards and well, invisible shields. It's the ultimate hidden world.
it really is.
And if you're listening to this right now, I mean, every single time you take a breath or turn the key in your car or even just turn on a space heater in your living room, you are actively participating in this crazy, complex chemical drama.
And what's so wild about that drama is how it completely flips our whole idea of like good chemicals versus bad chemicals.
Right.
Because the exact same molecules, literally the identical structures, they can be this life-saving shield in one part of the sky and then a deadly hazard down here where we breathe.
Yeah.
It all comes down to, um, well, context, concentration, and location.
Which is exactly what we're going to decode in this deep dive. We've got this great stack of environmental chemistry notes and diagrams, and the mission today is to look past all those typical buzzwords.
Yeah, like carbon footprint and all that.
Right, we hear them all the time, but we want to get into the actual granular chemistry of what's happening. And I think to understand how the atmosphere is breaking down, we really have to reverse engineer how it's built.
We do. We have to look at the architecture of the sky, basically.
Right.
So starting from the ground up to about 10 kilometers, you have the troposphere.
That's where we live, basically.
Yeah, that's where all our weather happens.
Yeah.
But if you push past that from like 10 up to maybe 50 kilometers, you hit the stratosphere. And right in the middle of that stratosphere, there's this really specific continuous chemical engine running.
You're talking about the ozone layer.
I am, yeah. Though, I mean, calling it a layer makes it sound like this cozy static blanket just draped over the Earth.
Right, like a bubble.
Exactly, but it's not. It's a really violent, dynamic chemical process. So up in that mid-stratosphere, you have regular oxygen gas, diatomic oxygen, or O2.
Which is the exact same stuff we're inhaling right now, right? Just two oxygen atoms stuck together.
Precisely.
Mm.
So you've got these O2 molecules floating around in the freezing cold upper atmosphere, and they are just getting absolutely bombarded by incoming ultraviolet radiation from the sun.
Just blasted by UV light.
Yeah, and this UV light, it's not just bright, it carries a massive payload of energy. So when a high-energy UV photon actually hits an O2 molecule, it acts like a microscopic scalpel.
Wow.
It has so much kinetic energy that it just shatters the chemical bond holding those two oxygen atoms together.
It just snaps them right in half.
It snaps them apart. So now, instead of O2, you're left with two solitary oxygen atoms. We call that monatomic oxygen, or just O.
Okay, got it.
But here's the thing about oxygen, chemically speaking. It really hates being alone. It's incredibly unstable and wildly reactive when it's solitary.
So it's looking for a partner immediately.
Within a fraction of a second, these solitary atoms go zooming off and forcefully collide with other intact O2 molecules that are nearby.
Ah, so one single O atom slams into a double O2 molecule, and 1 plus 2 gives you O3.
Exactly. O3 is ozone. That is the fundamental mechanism of how it's formed.
That's fascinating.
But there's a really crucial thermodynamics detail here. This specific reaction where they recombine, it's exothermic.
Meaning it releases heat.
Yes.
Yeah.
It releases heat energy directly into the surrounding environment.
Wait, really? Because you'd normally assume that the higher up you go, toward the void of space, the colder it gets.
And you do see that steady drop in the troposphere. It gets freezing. But once you hit the mid-stratosphere where this ozone engine is churning, the temperature actually flips.
It gets warmer.
It gets significantly warmer because you have this constant absorption of intense UV, the breaking of molecules, and that exothermic bonding releasing so much ambient heat. It's basically a planetary scale furnace fueled by sunlight.
Okay, so if the mid-stratosphere is this hot ozone furnace, what's going on right below it? Like in the lower stratosphere, maybe 10 to 20 kilometers up?
Well, the chemistry totally changes there, mostly because the raw materials change. The mid-stratosphere is acting like this massive UV filter.
Oh, I see.
Yeah, it absorbs the vast majority of that incoming radiation just to fuel the creation of the ozone. So by the time the sunlight actually makes it down to the lower stratosphere, it's already been stripped of all those high-energy UV photons.
So the lower layer is basically starved of the energy it needs to run that reaction.
Precisely. You don't have that UV scalpel anymore. Without it, the O2 down in the lower stratosphere just stays perfectly intact. And if you don't break the O2, you don't get the solitary O atoms.
And without the single pieces, you can't build the O3.
Exactly. So the lower stratosphere has virtually no ozone formation.
That is just incredible. The whole system relies on solar radiation acting as this perfectly placed trigger. We literally have a shield suspended exactly where we need it, built by the sun to protect us from the sun.
It's beautifully efficient.
But this brings up kind of a complication when we start talking about the stuff floating in our air down here. Before we go further, we really need to define what we mean when we use the word pollution.
We do,
Right.
because people throw that word around a lot in casual conversation. They tend to blur the lines between a pollutant and a contaminant.
Right.
But structurally, in chemistry, they mean very different things. A pollutant is strictly defined as a waste material generated by human activity that enters the environment and fundamentally harms living organisms.
It makes things hostile to life.
Yes. Yeah. Whereas a contaminant is just a substance that makes something impure.
Okay, so let me see if I have this right. If I take a glass of perfectly distilled water and I drop a pinch of, I don't know, sterilized table salt into it, I've contaminated it, right? It's not pure H2O anymore.
Right.
But if I drink it, I'm perfectly fine.
Exactly. It's a contaminant, but not a pollutant. But if you take that same glass and drop in some industrial mercury runoff well, now you've contaminated and polluted it because that mercury actively harms biology.
Oh, it makes a lot of sense.
And the severity of a pollutant isn't just, a coin flip of good or bad. It's calculated based on 3 intersecting variables.
Yeah.
Its chemical nature, its concentration, and its persistence.
Okay, let's break those down. Chemical nature, that's just the inherent identity of the molecule, right? Like carbon dioxide acts totally differently than aerosolized lead.
Right. It's the molecule's baseline personality. Is it highly reactive? Is it acidic? Does it bind to human tissue? That's the nature. Then the second variable is concentration.
The actual volume of the stuff in a specific area.
Yeah, the literal amount. And this is where the math gets really interesting. Because even a totally beneficial substance can cross this threshold and become a deadly pollutant if the concentration gets too high.
Interesting. And the third one was persistence.
Persistence is its lifespan in the environment. So does it just degrade harmlessly after a few minutes in the sun, or does its molecular structure let it hide in the topsoil for 10,000 years?
Wow. Okay. So nature, concentration, and persistence. With those rules in place, our notes divide atmospheric pollution into 2 main buckets: primary pollutants and secondary pollutants.
Right.
And primary pollutants seem to be like the immediate stuff, the unfiltered output of human society.
They are the direct exhaust. Whenever we burn fossil fuels or organic matter, primary pollutants are the raw waste that comes straight out of the tailpipe of the smokestack.
So we're talking about oxides of sulfur, like SO2, oxides of carbon, CO2, carbon monoxide, nitrogen oxides, plus unburnt methane, ammonia, stuff like that.
Exactly. Those are the frontline offenders, the initial ingredients just dumped right into the sky.
But the sky isn't just an empty storage unit.
No, not at all. It's this highly turbulent UV-soaked chemical reaction vessel.
Yeah.
So once those primary pollutants hit the open air, they don't just sit there, they react.
With what?
With everything.
Yeah.
Atmospheric water vapor, baseline oxygen, sunlight, and even with each other. These cascading reactions synthesize what we call secondary pollutants.
Okay. And this is where you get the really nasty stuff, right? Like sulfuric acid, nitric acid, complex organic stuff like pan and weight.
And ozone.
And ozone. Okay, hold on. This is a massive paradox. We literally just spent the first 10 minutes establishing that the ozone layer up in the stratosphere is this miraculous life-saving shield.
We did.
But now the notes are classifying ozone as a secondary pollutant, a toxic hazard. How can the exact same molecule be our greatest protector and a poison at the same time?
It is a brilliant paradox, isn't it? It perfectly illustrates that rule of concentration and location.
Okay, unpack that for me.
Up high, in the stratosphere, ozone is miles and miles away from biology. It's completely geographically isolated from us. So up there, it operates purely as a radiation filter.
Right.
But down here in the troposphere, down on the streets where we're actually walking around and breathing, ozone is simply not supposed to exist in high concentrations.
Because, like we said earlier, the UV light needed to naturally make it has already been filtered out.
Exactly. But human infrastructure creates this chaotic loophole. Cities pump thousands of tons of primary pollutants, especially nitrogen oxides and volatile organics, from cars right into the lower atmosphere.
Creating a giant chemical soup.
Yes, and when ordinary visible sunlight hits that specific man-made mixture, it triggers a chain of photochemical reactions that artificially creates ozone right at ground level.
And I'm guessing breathing O3 feels a bit different than breathing O2.
Oh, it is actively destructive. Ozone is an incredibly aggressive oxidizer. That crazy reactivity is what makes it so good at catching radiation high up. But when you inhale it, it literally attacks the delicate cells lining your respiratory tract.
Oh,
It
man.
chemically burns lung tissue, it triggers severe coughing, airway inflammation, and it's terrible for asthmatics. It even damages agricultural crops. So yeah, stratospheric ozone is essential. Tropospheric ozone is a biological hazard.
That is just wild. It's a stark reminder that the atmosphere is this huge, three-dimensional machine, and our surface emissions are just throwing a wrench right into the bottom gears.
That's a great way to look at it.
Which naturally leads us to probably the most debated element of our time, carbon. Because if location and concentration dictate everything, carbon is the perfect case study. It operates on two totally different timelines.
It really does. Let's look at the macro scale first.
Yeah.
Carbon dioxide, CO2. In popular media, CO2 is constantly villainized as this inherent poison, but chemically, that's just inaccurate.
Right, because if you step back, CO2 is basically the foundational life gas for the entire botanical world. It's as important to a pine tree as oxygen is to us.
Exactly. It's the backbone of a perfectly closed-loop biological engine. Plants take in atmospheric carbon dioxide and water. They use sunlight to crack those molecules open during photosynthesis, rearrange them into glucose for energy, and then they release pure oxygen as waste.
And then humans and animals just run that exact equation in reverse.
We do. We inhale their oxygen waste, we eat the glucose, and cellular respiration burns them for energy, exhausting CO2 and water right back into the air.
It's a beautiful self-sustaining loop. But even aside from biology, CO2 has a really vital mechanical job for the planet, right? The greenhouse effect.
Yes, it forms an atmospheric envelope.
So the standard analogy I always hear for the greenhouse effect is like a car parked in a sunny lot with the windows rolled up. The sunlight comes through the glass, heats up the dark seats, and then that heat can't easily escape back through the solid glass.
It's a classic analogy.
But on a molecular level, how does an invisible gas act like a solid pane of glass?
To understand that, you have to look at the wavelengths of the energy involved. When the sun blasts energy at the Earth, it arrives mostly as visible light and UV light. These waves are very short and tight.
Short wavelengths, okay.
The molecular structure of CO2 is essentially transparent to those short wavelengths. The incoming solar energy just passes right through the gas without interacting at all, hits the Earth's surface, and warms up the dirt and the oceans.
So it completely ignores the CO2 on the way in.
Right. But the Earth doesn't just hold all that heat forever. It radiates that thermal energy back out toward space. But here's the key. It doesn't radiate it back as visible light. It radiates it as infrared heat.
And infrared has a longer wavelength.
A much longer, wider wavelength. And the molecular geometry of CO2, which is a carbon atom flanked by two oxygen atoms, has this specific resonant frequency.
Uh-oh. I think I see where this is going.
Yep. When that longer infrared wave hits the CO2 molecule, it perfectly matches its frequency. The CO2 absorbs the heat energy and starts vibrating violently. It literally catches the heat. And as it vibrates, it eventually releases that energy again, but it scatters it in every direction, including right back down to the surface.
So it's basically catching the outbound heat and just bouncing it back.
Exactly. And honestly, a baseline level of this thermal trapping is totally necessary. If we didn't have that natural CO2 envelope vibrating and catching heat, the Earth's average surface temperature would plummet
How far?
to roughly negative 20 degrees Celsius.
Oh, wow. The oceans would just freeze solid.
But because of that natural greenhouse effect, our global average sits at a comfortable 15 degrees Celsius.
That's a huge swing, like a 35 degrees Celsius jump, which is over 60 degrees Fahrenheit just because an invisible gas is vibrating.
It's the ultimate Goldilocks scenario. But here is the crisis. Over the past 60 years, human industrialization has drastically overwhelmed that natural equilibrium.
Because we spent a century digging up ancient, stored carbon, coal, oil, gas, and setting it on fire.
Right. When we combust fossil fuels, we are artificially synthesizing colossal volumes of primary CO2 and pumping it straight into the air, rapidly thickening that thermal envelope.
We're basically adding trillions of vibrating molecules to the sky, trapping way more of that outbound heat than we should.
The physics are totally inescapable. More CO2 directly equals more retained thermal energy. And this continuous trapping is currently driving a global temperature increase of roughly 0.05 degrees Celsius every single year.
Now, to a layperson, that sounds like a tiny microscopic fluctuation. I mean, if the thermostat in my house goes up by a 20th of a degree, I wouldn't even notice.
But you have to scale that energy up to the mass of the entire global atmosphere, plus the oceans. A fraction of a degree globally requires an absolutely unfathomable injection of heat energy.
Right, it's a huge system.
And that trapped energy fundamentally rewires how the planet operates. It supercharges the weather, driving extreme, erratic meteorological events with way more ferocity.
Because, I mean, weather is really just the atmosphere trying to move heat around, right? So if you pump the system full of extra heat, the storms have to be exponentially more violent to move it.
Exactly. Furthermore, that ambient heat relentlessly melts glacial ice and polar snowcaps. That dumps massive volumes of fresh water into the oceans.
Which has to cause problems.
Two big ones.
Yeah.
First, it alters thermal ocean currents, which can spawn even worse tropical cyclones. Second, it fundamentally raises the baseline sea level.
The water literally has to displace something. It has to go somewhere.
And the inevitable conclusion of that is the submerging of low-lying coastal regions. It makes currently populated areas completely uninhabitable.
And it's just this slow-motion planetary scale consequence driven by a molecule that isn't even toxic to humans.
Right. CO2 won't poison you directly.
But if we flip the coin, carbon has a second face. And this one is an immediate, highly localized poison. Carbon monoxide. CO instead of CO2.
Yes, where CO2 is the byproduct of a functioning, well-ventilated fire, carbon monoxide is the byproduct of a suffocating fire.
Wait, it still comes from combustion though, right?
It does, but the mechanism is incomplete combustion. If you burn a carbon fuel in an area with plenty of oxygen, every carbon atom easily grabs 2 oxygen atoms. You get CO2.
Right.
But if you restrict the oxygen supply, like burning wood in a poorly ventilated room or running a generator inside a closed garage, the carbon atoms are starved. They can only find a single oxygen atom to bond with. So you get CO.
Okay, here's my question though. If I'm sitting in a closed room with a malfunctioning space heater pumping out carbon monoxide, the room is still mostly full of regular air. I'm still breathing in O2. So why does carbon monoxide kill me? Why doesn't my body just use the oxygen that's obviously still in my lungs?
Because it uses the terrifying elegance of our own biology against us. First of all, carbon monoxide is entirely colorless and completely odorless.
So you have zero warning.
Zero. You have no sensory awareness it's accumulating. And the real danger happens microscopically, right inside your red blood cells.
With hemoglobin, right?
Yes. Hemoglobin is this complex protein with an iron atom at its core. Its entire biological purpose is to travel to your lungs, grab onto fresh oxygen molecules, carry them through your bloodstream, and release them to feed your brain and vital organs.
It's like a tiny molecular delivery truck.
Exactly. O2 hops on in the lungs, hops off at the brain. But carbon monoxide acts as a hijacker. When you inhale CO, it hits the lungs and encounters that hemoglobin. But CO's chemical affinity for that iron core is hundreds of times stronger than oxygen's affinity.
Wait, really? Hundreds of times?
Yes. Then hemoglobin chemically prefers the carbon monoxide. It's intensely drawn to it. So the CO snaps into those receptor sites and bonds with incredible strength, physically blocking any oxygen from getting on the truck.
Wow.
And unlike oxygen, which naturally lets go when it reaches your tissue, the CO refuses to let go.
So the delivery trucks are hijacked, the doors are locked, and they just circulate through your bloodstream totally useless.
Exactly. You could be taking deep, panicked breaths of pure oxygen, but because your hemoglobin is saturated with carbon monoxide, none of it is transferring to your tissues. You experience systemic cellular suffocation from the inside out.
That is just horrifying. And because it's odorless, people don't even realize they're suffocating.
The onset of symptoms is deceptively mild. As the CO concentration rises in your blood, you just get a dull headache and a heavy sense of fatigue.
Which, if you're next to a heater on a cold night, you probably just like, oh, I'm getting sleepy.
People just assume they're tired. But as exposure continues, it escalates to severe breathing difficulties, neurological impairment, and eventually cardiac arrest and death. This is exactly why the foundational rule of indoor combustion is absolute ventilation.
Right. Never run a generator or a gas heater in an enclosed space.
Especially while sleeping.
It's crazy how dramatically the threat changes, just based on whether a molecule is missing a single oxygen atom. But, you know, carbon isn't the only element blasting out of our engines. We also have to look at what happens when natural impurities in our fuels hit the extreme physics of combustion.
Right, the synthesis of literal acids in the sky.
Let's talk about sulfur and nitrogen, because this brings us to acid rain.
Sulfur is a fascinating element. It's actually a natural component of the Earth's biological cycle. You find trace amounts emitted naturally by, like, bacterial decay of organic matter or big sudden releases during volcano eruptions.
So the atmosphere is used to processing a little bit of sulfur.
A little bit, yes. But human industry radically altered the scale. Roughly 80% of all sulfur dioxide, SO2, currently introduced into the atmosphere comes from one single source: burning coal and unrefined petroleum.
Because coal isn't just pure carbon, is it? It's basically fossilized swamp from millions of years ago. It's loaded with impurities.
Exactly. Heavily laden with sulfur. When you incinerate that coal to generate electricity, you're vaporizing those impurities too. The sulfur reacts with oxygen in the furnace, creating sulfur dioxide and sulfur trioxide, which just goes straight out the smokestack as primary pollutants.
And what happens if a human inhales SO2? Is it like CO?
Oh no. Unlike carbon monoxide, SO2 makes its presence very aggressively known. It's a colorless gas, but it has a harsh, violently irritating odor.
Like rotten eggs or matches?
Similar, yes.
Yeah.
When it contacts the moisture lining your respiratory tract, it immediately causes severe irritation, a choking sensation, and it triggers intense bronchial spasms. It's particularly dangerous for individuals with pre-existing asthma.
Okay, so sulfur is this dirty impurity we dig up.
Yeah.
But the notes say the nitrogen problem NOx operates totally differently. And honestly, it sounds much stranger.
It's a profound example of unintended chemical engineering.
Okay, let's lay out the baseline. The air you and I are breathing right now is about 21% oxygen and almost 79% nitrogen gas, N2. So nitrogen is literally everywhere. We're bathed in it.
Yeah.
And it's notoriously inert. It doesn't react with us. It doesn't catch fire. So how does an element that is so fundamentally stable suddenly transform into a toxic primary pollutant?
The mechanism hinges entirely on extreme, unnatural heat. The reason N2 is so stable is its molecular structure. The two nitrogen atoms are fused together by a triple covalent bond.
A triple bond? That sounds tough to break.
In chemistry, a triple bond is incredibly strong. It takes a massive injection of kinetic energy to shatter that bond and force the nitrogen atoms to react with surrounding oxygen.
In the natural world, what kind of energy does that?
Lightning. Under normal conditions, the only phenomenon energetic enough to crack an N2 molecule is the localized plasma of a lightning strike during a thunderstorm.
But humans figured out a way to mass-produce lightning.
Basically, yes. We built millions of high-pressure metal cylinders, injected them with explosive fuel, and ignited them.
Car engines.
Car engines and the massive boilers of thermal power plants. They're just burning fuel. They violently compress ambient outside air, which is mostly nitrogen, and subject it to temperatures so extreme that they replicate the physics of a lightning bolt.
We trap extreme thermodynamics inside an engine block, and the inert nitrogen is forced to react against its will.
Exactly. The heat shatters the triple bond, allowing the single nitrogen atoms to bond directly with oxygen, synthesizing nitric oxide, NO, inside the cylinder.
And then that NO gets blasted out the tailpipe.
Right. But the chemistry doesn't stop there. Once it hits the open air, the NO rapidly oxidizes further, scavenging another oxygen atom to become nitrogen dioxide, NO2.
Which the notes classify as highly toxic.
It is a severe lung irritant. This whole family of nitrogen-oxygen compounds, collectively known as NOx, is a huge driver of urban smog. But the most destructive phase of both these sulfur and nitrogen cycles happens when these gases drift upward.
Into the clouds.
Yes, they interact with the hydrological cycle. This is the genesis of acid rain.
Okay, so to contextualize acid rain, we first need to know what normal rain is. Because normal rain isn't perfectly neutral, pure water, is it?
No, normal rainwater is inherently weakly acidic. As a raindrop condenses and falls, it naturally interacts with the background levels of CO2 we discussed earlier. It dissolves a tiny fraction of that CO2, making a very mild carbonic acid.
On the pH scale, where 7 is totally neutral, where does normal rain sit?
Unpolluted rainwater typically registers a pH between 5.6 and 6.0. It's a gentle acidity that terrestrial ecosystems have adapted to over millions of years.
But when that raindrop falls through a lower atmosphere saturated with our primary pollutants, the SO2 from coal and the NO2 from cars, the chemistry gets radically aggressive.
The water acts as a solvent. It absorbs the sulfur dioxide and catalyzes it into sulfuric acid. At the same time, it absorbs the nitrogen dioxide and synthesizes nitric acid.
Wait, sulfuric and nitric acids? Those are hardcore industrial corrosive chemicals, and they're just being synthesized inside rain clouds.
Yes, and when that acid-laced rain falls, the pH plummets from the natural 5.6 down to roughly 4.0.
Now, to someone unfamiliar with the math, a drop from 5.6 to 4.0 might not sound catastrophic.
But the pH scale is logarithmic, much like the Richter scale for earthquakes. Every whole number drop represents a tenfold increase in acidity.
Tenfold. So a drop from 5.6 to basically 4.0 means the rain is practically 40 times more acidic than it naturally should be.
Exactly. And when precipitation that acidic hits the ground, it initiates a slow, grinding ecological collapse. It permeates the soil, leaching away vital nutrients like calcium and magnesium. It makes the earth hostile to forests.
And it runs off into the water, right?
Flows directly into streams and lakes. It fundamentally shifts the pH of the water until the environment becomes too toxic to support fish and aquatic insects. It even directly scorches plant foliage.
And it isn't just biology that suffers. If you pour acid on stone, eventually the stone loses.
We see profound structural degradation of human infrastructure. The calcium carbonate in limestone and marble is highly reactive to these airborne acids. Historic monuments are quite literally being dissolved.
Like the Taj Mahal, right? The notes specifically mention it. You have this pristine, world-renowned white marble structure in India, and it is being continuously etched and degraded by sulfuric and nitric acids that were forged in the engines of cities miles away.
It is the ultimate manifestation of the persistence and widespread nature of secondary pollutants. Pollution doesn't respect borders.
Not at all. The emissions you generate in one place will just fall as acid on another.
Right.
So we've mapped out a profoundly alarming system here. We've got a greenhouse effect thickening our thermal blanket, localized asphyxiation from carbon monoxide, and literally corrosive acids raining from the sky. But atmospheric chemistry isn't just a tool to diagnose disasters. It's also the mechanism for our salvation, right?
Oh, absolutely. The exact same scientific rigor that lets us identify the molecular destruction provides the blueprints to reverse it.
How do we engineer our way out of this chemical corner?
The solutions generally fall into three categories: localized mechanical intervention, fundamental chemical substitution, and systemic structural policy.
Okay, let's start with the mechanical intervention, because this is a piece of technology almost everyone owns, but very few people actually understand. The catalytic converter.
Yes, it sits right underneath your car, in the exhaust line.
I've always thought of it as a sort of chemical undo button, but how does it actually operate on a molecular level?
It is an absolute marvel of solid-state chemistry. Before the chaotic, toxic exhaust gases the CO, the unburnt hydrocarbons, the unnoxed can exit the tailpipe. They're forced through this heavy metal canister.
And what's inside?
A dense ceramic honeycomb structure designed specifically to maximize surface area. And that honeycomb is plated with rare, highly reactive precious metals, primarily platinum, palladium, and rhodium.
Okay, the catalysts.
Right. A catalyst is a substance that dramatically accelerates a chemical reaction or lowers the energy needed for it to happen without actually being consumed itself.
So as the blisteringly hot, toxic exhaust gases get pushed through this tight honeycomb, they physically scrape against the platinum and palladium?
And in those tiny milliseconds of contact, a series of rapid molecular translations occur. Let's look at carbon monoxide first. As the CO hits the hot palladium, the catalyst forces it to undergo an immediate oxidation reaction.
Meaning it has oxygen.
It violently strips ambient oxygen from the exhaust flow and forces the CO to accept a second oxygen atom. It transforms the deadly CO into CO2.
Now, obviously, we established CO2 as a greenhouse gas driving climate change, but in the immediate, localized context of a crowded city street.
It's a massive harm reduction step. CO2 won't asphyxiate the pedestrians walking past the tailpipe.
Exactly.
The converter performs a similar oxidation on the raw, unburnt hydrocarbons, the fuel vapors that fail to ignite. It fractures those long carbon chains and forces them to combust completely into standard carbon dioxide and harmless water vapor.
But I think the most impressive trick is how it handles the NOx, the stuff causing the acid rain.
Yes, it reverses that lightning in a bottle effect. It operates a reduction reaction. As the NO and NO2 molecules hit the rhodium catalyst, the metal briefly grabs hold of the nitrogen atoms and literally rips the oxygen atoms away.
Wow.
Then it forces the isolated nitrogen atoms to bond back together with each other, resynthesizing the incredibly strong triple bond of N2 gas.
It literally stitches the nitrogen back into its inert, harmless state,
Yeah.
exactly as it was before the engine sucked it in.
It unmakes the primary pollutant right before it escapes. Hot, poisonous gases enter the honeycomb, and a mixture of CO2, water vapor, and harmless nitrogen gas exits. It's an incredibly elegant mechanical filter.
But the mechanical filter is still just treating a symptom.
Ugh.
We also have to address the root cause, the chemical fuel itself. Why are standard fossil fuels so inherently difficult to burn cleanly?
It really comes down to molecular complexity and inherent impurities. Like we saw with sulfur, digging organic sludge out of the earth gives you a chemically messy product. But even heavily refined petroleum is problematic because of its complex architecture. The molecules are built as these long, branching chains of carbon and hydrogen.
And I'd imagine the longer and more tangled the molecular chain is, the harder it is to ensure every single atom finds oxygen during a split-second explosion inside a cylinder.
Exactly. You need perfect timing, perfect pressure, and perfect oxygen ratios to achieve complete combustion of a complex molecule. In the real world, engines are imperfect. Those long chains snap and fragment, which results in soot, unburned hydrocarbons, and carbon monoxide.
Which brings us to the chemical substitution part. The structural solution requires alternative, simpler fuels.
Right. Alcohols like methanol and ethanol or heavily refined biodiesels. The defining characteristic of these alternatives is their molecular simplicity. An ethanol molecule, for instance, is short, symmetrical, and crucially, it already contains oxygen atoms within its own structure.
So because it's smaller and simpler, it's just way easier to tear apart and burn completely during the cycle.
Complete combustion is so much easier to achieve. When you burn a simpler molecule, you dramatically reduce soot, you virtually eliminate unburned hydrocarbons, and you starve the process that creates CO.
So we have the mechanical fix with converters and the chemical fix with cleaner fuels. But implementing these on a global scale requires the third avenue, systemic structural policy.
Because you really can't solve a planetary atmospheric crisis purely through individual consumer choices.
No, it requires coordinated top-down legislative intervention. I mean, driving a heavily polluting vehicle feels like a simple daily necessity to most people, but structurally, it's a localized emission of toxic hazards that collectively drive a global shift.
And since the atmosphere is a shared, borderless resource, maintaining its chemical integrity demands vast, long-term government planning.
Let's objectively examine the structural mandates the note suggests to reorganize this whole system.
The first mandate focuses on immediate harm reduction regarding existing tech. Governments must regulate the specific chemical quality of the fuel being sold, ensuring anti-knocking agents and refining standards are strictly met.
Right.
Furthermore, they have to legally mandate engine efficiency standards, and most critically, require the installation and maintenance of catalytic converters on all combustion vehicles.
Basically, legally enforce the use of the chemical undo button.
Yes. The second mandate targets the fuel supply chain. It requires government to actively subsidize and promote the infrastructure for those simpler alternative fuels, the ethanols and biodiesels, to begin phasing out complex petroleum.
But even with cleaner fuels and perfect converters, you are still generating massive amounts of CO2. Which brings us to the third mandate, aimed directly at the greenhouse effect.
Exactly. To arrest the accumulation of the thermal blanket, structural policy has to dictate a transition away from combustion entirely. A calculated phase-out of carbon-emitting engines in favor of widespread adoption of battery-powered electric vehicles. Zero localized exhaust emissions.
And the final mandate steps away from the vehicle entirely. It looks at the actual design of human habitats, urban planning.
Yes, governments must heavily invest in and provide highly efficient electrified mass public transit systems in densely populated areas. The ultimate goal is to fundamentally reduce the baseline number of individual localized emission sources operating at the same time.
It's a massive, multi-tiered approach. Engineering the tailpipe, simplifying the fuel, electrifying the grid, and redesigning the cities.
Because the chemistry of the atmosphere is totally integrated. You can't solve the localized ozone problem without addressing the NOx emissions. And you can't solve the NOx emissions without altering the thermodynamics of the whole transportation system.
We have unpacked an immense amount of atmospheric architecture today. I mean, we started by looking 50 kilometers straight up, observing how the violent energy of UV light shatters oxygen to forge an ozone shield, literally making life on the surface possible.
And we saw how that exact same chemical reaction, when it's artificially replicated at ground level by our exhaust fumes, creates this highly reactive hazard that scars our lungs.
We explored the dual nature of carbon, how the slow, massive accumulation of CO2 is acting as a planetary thermal trap, absorbing the Earth's escaping heat, and then how its starved cousin, carbon monoxide, acts as a stealthy, localized hijacker of our red blood cells.
We detailed the inadvertent atmospheric laboratories inside our engines, where extreme heat and buried impurities forge destructive sulfuric and nitric acids, acids that alter the pH of our rain and dissolve ancient monuments.
But we also illuminated the sheer power of applied chemical engineering, how a small platinum-coated honeycomb can force toxic molecules to unreact, stitching nitrogen back together before it ever hits the open air. It really is this constant invisible balancing act of concentration, location, and molecular structure.
It truly is. But, before we wrap up, if we look closely at that structural mandate regarding the transition to battery-powered electric vehicles, the one meant to solve the CO2 crisis, it really requires us to apply the exact same critical lens we've used throughout this entire deep dive.
How so?
Well, electrification brilliantly eliminates the localized emission of primary atmospheric pollutants. The tailpipe is gone.
Right.
But as atmospheric chemistry continuously teaches us, every massive human intervention involves an exchange of materials. If we are preparing to replace 1 billion internal combustion engines with 1 billion massive, high-density chemical batteries relying on lithium, cobalt, complex polymer electrolytes.
What new unforeseen variables of chemical persistence are we introducing into our environment?
Exactly. If we solve the chemistry of the sky, what new chemistry are we burying in the soil? We spent a century reverse engineering and solving the thermodynamics of the tailpipe. But managing the physical life cycle, the degradation, and the persistence of billions of complex chemical batteries.
That might just be the defining chemical challenge of the next century.
I think it will be.
The chemistry never stops reacting. It just changes its molecular state. Thank you for joining us for this deep dive into the invisible world around you. Keep looking past the buzzwords, keep asking how the machine actually works, and we will see you next time.